Okay, so our next speaker, Mustafa Kemal Döner, is Gravitational Entanglement Evidence for the Quantization of Spacetime. Indeed, we wait your verdict.
Thank you. First of all, I would like to thank you to the organizers for giving me this chance to talk. So I'll basically present our paper, which is recently published, and it is directly focusing an experiment, a total experiment. And actually we have seen yesterday by Mazumdar himself. We can just show that one, yes. The total experiment is basically like this, two quantum particles with equal mass, and with the distances shown here. And they are experiencing this double Stern-Gavek apparatus, and then having these trajectories, and especially the closest trajectories, they have this interaction between them, the classical one, by the F graph, you can see, Newtonian gravitational interaction. And after this point, they claim this thing, for two, it is impossible for two quantum systems to develop entanglement out of classical field, and by that, in their experiment, in their thought experiment, this entanglement is induced by the gravitation. This gravitation also needs to show this quantumness in it. So basically, they are saying that entanglement is quantum, so the gravity in its nature should be quantum as well. But in here, with this paper, we are presenting a counterexample to this, and we are actually saying the against of this thing. This gravitational entanglement is evidence against semi-classical theories. We are making a counterexample to this, and we are using a trajectory approach which is taking its roots from the de Broglie-Bohm theory, and we are choosing this thing because it is actually really close in the speed. It's closer to the mean field approach, and we are not the first ones to do this thing. Actually, Reggio and Anderson, they already proposed a similar idea, but they didn't elaborate that much after this. But we will see that in this paper we elaborate it a little more. So let's start talking about this model, and let's start by asking this question: how does one model the effect of quantum matter in a classical spacetime curvature? To answer this we can see that in the first equation, as an answer to this question, it is basically the semi-classical Einstein equations. And here. So on the left side, we can see that by the Einstein tensor, it is basically describing the classical spacetime curvature. On the right-hand side, we have this stress energy operator, which is residing there as an expectation value of it, and it is describing the quantum matter in this classical spacetime structure. And for non-relativistic case, as we can see in the second equation, for non-relativistic case, it is basically Schrödinger-Newton equation, and by using that, we can write our semi-classical potential as in the second equation. And for the sake of our model, mostly we will avoid using self-interactions because they will not show anything that is important for us. On the other hand, if you look at the situation, we have perturbative quantized gravity, which we can see on the third equation. And the difference between these potential terms are, we can directly see, for example, in the second equation, when we look at the first term, it is depending on the first particle coordinates, the expectation value of the second one, and vice versa. And on the other hand, quantized gravity case, the interaction between these masses, we need to look, we can see that it is really depending both of the coordinates of the particles. This is important because for semi-classical case, if we have a system initially unentangled, we can see that semi-classical gravity cannot show any entanglement afterwards. On the other hand, for quantized gravity case, it can show the entanglement between them. So let's start our model. This is the introduction. So we are thinking a model, and in our model we will use this Bohmian trajectories, and they are basically source. They are gravity sourced along these Bohmian trajectories. And now let's start discussing about this model. The first thing, it is very obvious for the particle trajectories. We are basically using the very famous tool of the Bohmian theory, Bohm theory, which is guiding equation, and it is basically describing the dynamics of these trajectories. On the other hand, we have this potential term, which I have written down as equation 5 as BBB, and it is a function of coordinates and at the same time the particle trajectory coordinates. So, and we can see even now, even with this equation, we can see the similarity of this potential to the quantized gravity potential. And with some, if we can choose for the third term, if you can choose gamma 0 as gm1 m2 divided by q1 minus q2, and with this arrangement we can say that this potential term is also obtaining the same phases as like the quantized gravity case. So we can conclude that our model with the Bohmian trajectory framework is really showing the similar predictions for classical trajectories and gravitational phase shifts as the quantized gravity. So we need to take another step because we want to relate our model to the semi-classical gravity, and by that mean field we start to build up this hybrid model, which we call mean field trajectory hybrid model. I know it is long, but I mean I had no choice. So let's go on. So with our developed Bohm trajectories, we now start to build up our hybrid model. And for this case, I think that the best way to demonstrate this connection is starting with the n-particle Schrödinger equation. And the important thing in here is this. We are now introducing this parameter R. This parameter R is really important for us because it will take these values between 0 and infinite. And by these values, it will show this hybrid instrument. And it will interpolate between quantized gravity and semi-classical gravity. Okay, so if as a result, as you can see in here, especially, as a result, in here we can see that this potential we are describing by our model is basically mimicking, for the R goes 0, it is basically mimicking the quantum limit, quantized gravity, but it becomes a quantized gravity potential, and we already showed that it is basically equal. And on the other hand, for R goes to infinity, it mimics like a semi-classical case. So after that we can write down our potential this VR as like this. It's a function of coordinates at the same time, trajectory coordinates and the wave function itself. On the other hand, right hand side of the equation, we are seeing lots of different functions. Let me just elaborate a little about these functions. For example, this one is f regularization function, which is for r goes to 0, it will take the value of 0, and for the for r goes to infinite, it will take the values of 0. For r goes to 0, it will take the value of 1. And by that, we can see that this potential, this VR, really interpolate between classical and the quantum reality. So let's continue a little more. Why semi-classical limit? Because it is just a Ehrenfest theorem, and by the Ehrenfest theorem we can see that the exact equality of the expectation values is giving us the limit, and with this theorem we can really connect, make the connection between for our situation and make the classical part classical limit. And after making some approximations, this approximation, for example, in here is Qi is, for our case, with our approximations is very equal to the coordinates, let's say Ri, and by that we end up with this Newtonian equations of motion. So now this is. In the beginning, I have already shown the experiment itself, but now I am showing in a little more details. This is the same experiment by them. So, in here, in the figure, we can see that two particles, two quantum particles, they have this distance between them, big delta x, and the superpositions of them, they have this small delta x. And by the double Stern-Gerlach apparatus, they are experiencing these combinations of trajectories, which is in total 4 of them, and this trajectories is depending on their eigenvalues, and here you can see them. And the UI, U12, S12, they are basically our trajectories and the coordinates of our trajectories. So let's make let's take another step and continue. So, I already told you that mostly we will ignore the self-gravitational terms because they are not really giving us any valuable contributions. And assuming that the particles have the same mass, and looking at only the interaction between the particles, we can write down a little more simplified version of our VR, like this, in the equation 10. And I think I forgot to talk about this function kind. This function kind, we call it characteristic function, and it is basically another, it's a limitation function, let's say. So, after this, we start assuming some things. For example, if you can see in here, in the figure, the time particles spending, okay, the time particles spending in their trajectories, let's call it tau, and the time they are spending in the Stern-Gerlach apparatus, let's call them tau A. Assuming that tau is way bigger than tau A, we end up with this trajectories in here. And with this trajectory, and after an integration of VR, we end up with this phase terms. And we take another more step, and in here, for example, we make these choices for free spreading of the, avoiding the free spreading of the wave function. By that, we limit it, basically. And we already made, again, we are making this assumption. It is very it is basically the same assumption we did before for Qi to Ri, and we are just doing it for the trajectories now. And with the R equal to this, we have already seen it many times. We can write down our phase term according to these trajectories. And after this, to make our life a little easier to understand the situation in here, we start to defining these phases. For example, global phase are the up and down in here, you can see. And we also define these other terms, which is the relative term or relative phases, as like this. And for looking at the situation a little more neatly, we also define this average phase term. And the next. So, by considering all these phases, we come up with these pilots. In the first one, we are talking about the y wave function, which is actually the most important thing for us because it is the closer one to our situation. And other than that, we have this other possible cases. And I think I am losing some time, so let's go back to the experiment itself. So we can see from yesterday, Mustafa was already talking about this. He's talking about his famous, in their famous Witten's entanglement function, entanglement Witten's function. And we are just, in here, we are just implementing our phases into this function. And in the end, by making these arrangements, we find this. And if you look at the graph, I'm just skipping quickly. The values bigger than 1 is basically showing us the entanglement. And values lower than 1 is basically showing that initially is basically showing the separated wave functions. And we can take a little more. We can look at the general treatment of this thing. And this is from another paper. And in here, they are talking about, actually they are doing the very similar thing, but they are making a more general treatment, and they are talking about the small and the maximum, the entangled case. And with our phases, with our model, we have shown that for both of the functions, we are really getting the entanglement. And in the end, we have reached our conclusions. So, I think reading these conclusions will summarize everything. We have presented a model for a relativistic quantum system on a classical spacetime, where the curvature of spacetime is sourced by the wave function and the particle trajectory. Except r goes to infinity. This is the problem, but it is the usual thing for the situation. But the second conclusion is, we have shown that this model results in gravitational phase shift for which the presented can find entanglement. And we showed this thing for all the witness wave functions. And this is and as a result, we just unquantized the entanglement between the two particles again, and shown that for a model taking its root from a classical structure, we can also show this entanglement in the end. Thank you.
We're out of time limit, but if there's one quick question, John.
Well, may I just, without taking the time, say, just to clarify the logic, in the final conclusion, we would say in English, I'm a philosopher, a man of words. You have an explicit counterexample to the claim that gravity must be quantized in order to get entanglement. Your counterexample is showing that gravity can be unquantized and we get entanglement. And this is really in slide 11, the left side where R is going towards, right? You've got W greater than 1 in the left side of this diagram. This is the good stuff.
Yes,
showing that
definitely.
with the
Yeah.
trajectories we've got a sort of mediation between the two halves. So those theorems that say you have to have degrees of freedom in order to get entanglement, degrees of freedom in the gravitational field, in a sense your trajectories are like the extra stuff that gives the mediation.
Yes, and actually, I mean, this is small talk. I would like to emphasize more, but I couldn't put in here, and maybe because of that, it is not that obvious. Yes, we have shown that, and we have shown these things by using these trajectories, and these trajectories, actually, if you look at I mean, this is a little more Bohmian perspective, but they are using these conditional wave functions. And with these conditional wave functions, they can really explicitly show the entanglement between the subsystems. And this is the crucial part, and we are using that and putting and really playing their game, and in the end showing that yes, there is an entanglement, and yes, we are showing it just by using the very classical, structure. And in the end,
good. Many thanks, and let's thank our speaker again.